Good morning. Thank you for joining me for this video. I am Mr. Esh and we continue with the topic of derivatives today by talking about logarithms. When we're looking at the derivatives, these are the derivative forms we need to be aware of because there are specific types of derivatives when it comes to logarithms. If you have something which is a natural log, in this format, where a could represent some sort of a coefficient, when you do the derivative of something like this, natural log, a parentheses and an x, but with a coefficient, you're basically just going to get 1 over x as your answer over here, the derivative of this. And I'll show you why soon. I'm just laying you out the framework for what we'll be looking at today. The other type of derivative you need to be familiar with is this one. If you're looking at anything which looks like this in a basic logarithm form, you can rewrite it as something like this: natural log x over natural log b. It can be represented in this format over here, natural log x over natural log b. But what exactly is the derivative of something which looks like this? It would be this: 1 over x ln b, and I'll show you momentarily why that is. This right here is a number 2 one which we look at, number 2 derivative for this video. And let me show you the last style of derivative that you need to be aware of, and it is this one. If you're looking at something which looks something like this, a power function, the derivative of this is going to be bx ln b. That'll be the derivative of this type of question. If however you had something which looked like this in terms of the same type of power function, b to the minus x, you can see your answer would become b to the minus x ln b. And I'll show you all of these four in a little bit more detail soon. Let's look at this one over here. When we do the derivative of something which looks like this, basically what happens to the a disappears, doesn't it? You don't see a over here in the answer, and I'll show you two reasons why. You can write natural log using the properties of logarithms. Natural log ax can be written as natural log a plus natural log x. You know, this right here is a variable component, this right here is just a constant. If you did the derivative of this expression over here, this expression right over here, look what you get: derivative of natural log a, which happens to be a constant, plus the derivative of natural log x. When you do a derivative of a constant, it's always 0, but when you follow the same scheme over here for natural log x, you must end up with a 1 over x, therefore you get as your final answer 1 over x, as you see over here. But the other way of looking at this is using the chain rule. If supposedly u was equal to a, if u is substituted for a, then you know f of u is equal to ln u, right? F of u is equal to ln u. Now we just have to do the chain rule over here, and look where derivative with respect to u, you have ln u, and then the derivative with respect to that x, you'll have an ax. Now when you do the derivative of these individually, ln u follows basically the similar form as this ln x. You get basically a 1 over u by means of this template scheme. And then the ax is just like a natural derivative here of a polynomial. The coefficient of x is a and x is to the power of 1. 1 multiplies with a, and then the exponent is reduced by 1. You essentially get left with just an a. So your final answer is a over u. But when you resubstitute back for the u, and the little error I made over here was that u was supposed to be equal to ax over here, because ln u, I mean your substitution here is ax, not just a, but it's an ax. Alright? When you resubstitute back for that u, you get a over ax, and then when the a's cancel out, you get left with 1 over x. So let me just state that again. When you did the substitution over here, u was equal to ax. F of u is equal to ln u, and then you come down here to the chain rule, derivative with respect to u ln u, and the derivative of u with respect to that x is ax. When you do the derivatives over here, you get 1 over u times a, you get a over u, but a you resubstitute back for ax, you get a over ax, and you get 1 over x. So you basically ending up with both schemes as this. So essentially the point I'm trying to make over here is when you're doing the natural log of something which looks something like this, the a will disappear and exactly the x variable will show over here in a reciprocal form. Now let's look again at something like this. You know, when you do the change of base formula in the properties of logarithms, you can just write this ln x or ln b. Now supposedly we have to take the derivative of this, because this is what we're talking about, something which looks like this, and we have to see what the derivative of that is. Then you're basically doing ln x or ln b. And look over here, this ln b is like a coefficient. You can write 1 over ln b, natural log b, times the derivative of ln x. All I've done is take this coefficient, which is a 1 over ln v, and I brought it out over here, and I've rewritten over here. Now you'll just use the same scheme for this. You'll get 1 over ln b times 1 over x, and your final derivative over here, as I showed you in the previous image at the very beginning, is 1 over x ln b. So this right over here will represent a derivative of something which looks like this. So that will be the template scheme you'll use for something like that. We look at the power function next in a little bit more detail, then we look at some solved examples. Again, the power function looks something like this. If you're taking the derivative of this, you know you should be getting something which looks like this. There's not much to say with regards to that other than that anytime you see a question like this, you're going to be presenting a derivative which looks something like this. But there is something to be said about something which looks like this, b to the power of minus x. If supposedly you imagine if b here represented e, base e, you can rewrite this as this, e to the minus x. Once you've done e to the minus x, right, you can think back to the derivative which you have for the exponential base. You know, e to the ax is always equal to ae to the ax, and you can follow the similar scheme over here. This minus 1 can come right over here, and the ax can stay the same. You'll get minus e to the minus x. But then you can resubstitute back the b for the e, and you can think of it as minus b to the minus x. But you still have to do the derivative of this, and then when you do that, you get minus b to the minus x, and then you can still put the natural log b, because the natural log b must come along with the derivative. And that right here will be the derivative of something which looks like this with a positive exponent. And for something which looks like this, the power function with the minus exponent, you'll have something in terms of your derivative looking like that. So now let's look through some examples. Over here on the top, I've laid out the derivatives as I've addressed already in terms of their templates. The schemes are over here on the top. We're going to start with some very easy questions, and we'll just go to the very trickier ones. And they're not, the tricky ones are actually easy. The whole subject on this logarithm derivative is not hard at all. If you look at this question over here, natural log of 5x, you know by very definition it should just come out to 1 over x, but let's just use the chain rule. If u was equal to 5x, then we know f of u would be equal to ln u, and then we did the chain rule, derivative with respect to u, ln u, and then derivative with respect to that x, 5x, you'll get 1 over u times 5. The derivative of 5x is 5. And then you get 5 over u, and you get 5 over 5x when you resubstituted back the u value, which is 5x, and you'd get a 1 over x. So that right over here is done. So anything which looks like this, a very simple case where the a is just a mere coefficient, you can make the coefficient disappear and go directly to 1 over x. So these are the simple cases. But in those cases where the item over here in the parentheses is like so inherently attached to the variable, you have a composite function, then you can't really get away with this simplicity over here. But let's look over here. Log base 3x, it'll be something which follows this scheme. You know you're looking at something which looks like this using the change of base, natural log x, natural log 3. And when you do 1 over ln 3 derivative of natural log x, all I did was take the coefficient out. 1 over natural log 3 is a coefficient. Then you do natural log x multiplied by that coefficient. You know this is 1 over x. You know at the end you'll get 1 over x ln 3, and you'll be done. So this question is completed. Let me just make the same type of question a little more tricky in appearance only. Tricky, but it won't be tricky at all, because you have to understand the effect of the a. The a disappears. See this a over here? These are a's here, and a coefficient will disappear. We should still get the same answer, but we'll work it out as if we were assuming we shouldn't get the same answer, but we will still get the same answer. Let's imagine this is a composite function, but it's really actually a simple case, not a very difficult case. But let's say u was equal to 2x, and then we proceed with f of u is equal to log base 3 of u. Then if you look at the change of base formula, you can look at it in this way. You have natural log 2x over natural log 3, and we're doing the derivative of this. We can just bring the natural log 3 out, and now we're doing the chain rule over here. We can say we have right here, see ln 2x became ln u because we substituted u for that. You could have also had said right here log 3u is also the same thing as ln u. Same thing, and I'm putting over here. And then derivative with respect to its x was 2x. When we simplify this, we get 1 over ln 3 natural log u comes out as 1 over u, and the derivative of 2x is just a 2, not an exponent here, but just a 2. And then you basically end up getting over here basically 2 over ln 3, and then you have to substitute back here for the 2x. The 2's cancel out, and what do you get? You get 1 over x ln 3, and you get exactly the same thing. So when you come over here, right over here at this simplified answer, I want to just transpose the answer so the picture is not cut off. When we come over here, and then what do we get? The 2's cancel out, and on the bottom we had x ln 3, and this right here was our answer to this question right over here. And you can see both of these are the same exactly. Look over here. This right here is exactly the same as this over here. This 2 over here made no difference whatsoever, because it kind of followed this case. The coefficient 2 over here of this variable x disappeared, and you see it disappear over here. I did it the more elaborate way when I didn't have to, but I did it the more elaborate way to show you why it disappeared. Let's look at some more examples. Our question is this right over here. The product of two functions. Here's one function f, and here's g function over here. We have to use a product rule, and you will just go directly to the template. The g function, which is ln x, multiplied by the derivative of the f function, which is e to the x, plus e to the x, multiplied by the derivative, which will occur, of the g function. We take this to the next level. Ln x multiplying by the derivative of e to the x is just e to the x, easy. And e to the x multiplying by the derivative of natural log x, which is just 1 over x, as you see right here, 1 over x. You bring everything together, you get ln x e to the x plus e to the x over x. Look for a common term. E to the x is a common term. Isolate e to the x, and you get in the parentheses ln x plus 1 over x, and you're done. Not a hard question. Let's look at this. The quotient of two functions, a rational function. We have the f function here on the top, the g function on the bottom. We have to use a quotient rule over here. We'll do the g function, which is x squared, multiplied by what will be the derivative of the f function, minus from that the f function and the derivative of the g function, divided by the g function squared, which will be x to the 4. X squared is x to the 4th. Now in the next step we solve it out. We have x to the squared on the top, and derivative of natural log x is just 1 over x. Minus natural log x times the derivative of x squared is a 2x over x to the 4th. You see this x over here? It can cancel out with this and make this x to the 1. What do we get left over here on the top? We get x minus ln x 2x over x to the 4. All of these x's are common. You can cancel them out and reduce the denominator to a cube. So what you end up getting is a 1 minus 2 natural log x over x cubed. 1 minus 2 natural log x over x cubed, and this right here should be your final answer. Completed. Maybe the algebra part was more difficult than the actual derivative part, but remember again, the whole purpose of these derivatives is to determine the instantaneous rate of change. It will give you the slope of the tangent line, that specific point on the curve for this function where you are interested in determining its rate of change. That's why we're bothering with all the derivatives. These are how you determine the slopes of these curved lines. So this question over here should not be too hard. We have a composite function. We're thinking about the chain rule, but once we separate the composite from the parental function, we'll have a product rule come into place. So we should start with the substitution where u is equal to these hyperbolic functions. Then f of u must be equal to ln of that u. So you go directly to the chain rule. Derivative of u with respect to u is ln u, and then derivative of that with respect to its x is the cosine hyperbolic and then sine hyperbolic, which are in the product relationship. So now you got to bring in the product rule. Here's your f function, here's your g function. Let's go directly over here to this next step, ln u, and now we do the chain rule. You're going to do the g function, sine hx multiplied by the derivative of the cosine hx, which is your f function, plus the cosine hx multiplied by the derivative of the g function, sine hx. And look, we're just going to complete this. Natural log u is a 1 over u, and here you're going to get sine hx multiplied by the derivative of hyperbolic cosine, which is a sine hx. You get a sine h square x. You remember this from the previous video. The derivative of hyperbolic sine is a hyperbolic cosine. You get a cosine h squared x. When you write this in the final form, you have to resubstitute for u. you get hyperbolic sine squared x plus hyperbolic cosine squared x all over your u substitution, which is right over here. Hyperbolic cosine hx times hyperbolic sine hx, and you are done. Let's write over here in a more clear answer, in a more clear format, our final answer, so you are able to see it. Hyperbolic sine squared x plus hyperbolic cosine squared x divided by our substituted u, which is just hyperbolic cosine times hyperbolic sine, and this right here is your final answer, right over here. Final answer. So let's look at this question over here. We have a quotient over here. Rule applying for a rational function. You have a power function on the top and you have a regular polynomial here on the bottom. You have to use the quotient rule template. You'll do the g function multiplied by the derivative of the f function minus the f function multiplied by the derivative of the g function, all divided by the g function squared, which is x to the power of 4. Now look over here, we have to bring in now the derivatives. The derivative of 2 to the power of x will follow right over here. It will be 2x ln 2 minus 2 to the power of x times the derivative of x squared, which is 2x all divided by x to the power of 4. Let's think about what we can isolate. We have 2 to the power of x, 2 to the power of x. We have some variable here, x, which can be isolated. We can isolate an x and we can isolate a 2 to the power of x. This right here, x times 2 to the power of x, goes over here, x ln 2 times, and it goes right over here 2 times. And you can see all of that divided by x to the power of 4. You can cancel out this x right here and you can convert this into a 3. So you end up with a final answer, 2 to the power of x times x ln 2 minus 2 divided by x cube, and you are done. Interestingly enough, these right here, the natural log derivatives, are more commonly seen than these ones. They're just not very common at all. But this is much more common, and you'll see it more frequently. But let's look at this question over here, the rational function. We have a quotient rule kicking in over here. We have our f function here and the g function here, and we have to apply the quotient rule template. The g function multiplied by the derivative of the f function minus the f function multiplied by the derivative of the g function, which will be seen in the next step, divided by g squared. See, x squared. Now let's come over here. The derivative of log base 2x will be just right, exactly what you see, 1 over x ln 2. That's what you'll get. It'll transform into 1 over x ln 2 minus log base 2x times derivative of x is just a 1. And then you have this over x squared. Look where these things cancel out over here. So you end up getting 1 over ln 2 minus log base 2x over x squared. Now let's enter the realm of some of the realistic type of questions you'll see. We look over here, we're doing a natural log of a root x, and you know we're seeing a composite function. And these are the types of derivatives you'll see more frequently of the natural log variety. But you don't have an ax, you have a composite over here. You have to do a substitution. If u is equal to root x, then f of u must be equal to natural log of that u. And you have to now carry this using the chain rule. Derivative with respect to u, you have ln u, and then the derivative with respect to that x, you have root x, and then natural log u is just a 1 over u multiplied by 1 over 2 root x, because you know the derivative of this is 1 over 2 root x. Now look over here, resubstitute back for u. What was u? Root x. You're getting 1 over root x times 1 over 2 root x. When you simplify all of this, root x times root x is just an x, and with that 2, you get a final answer of 1 over 2x, and this answer is completed. I purposely put this here in a single line because I want you to contrast this to what you see over here. Now the derivative of all of natural log x within a square root. You see how vastly different these two questions are? Here you still have to do, you have a composite function, and here you have to do a substitution, but you'll do a different substitution. Look, if u is equal to ln x, then f of u is equal to root u. Look over here, the substitutions. F of u here was a root u, here f of u was an ln u. So you're seeing a different substitution, but you're still using the chain rule. Now let's do the chain rule over here. Derivative with respect to u, you have a root u, and now derivative with respect to x, you have an ln x. And you can compare it to exactly what you see over here. Open this up. Root u is a 1 over 2 root u, and natural log x derivative is always 1 over x. You get 1 over 2x, and resubstitute back for root u, which was what? Ln x. and here's your final answer. You can compare this answer right over here to this answer right over here, and you can see how vastly different they are simply with the placement of the radical sign. But this is more within the realm of realistic type of questions you'll see with this type of topic. We end our video and this topic on the logarithm derivatives with this last question, and it will prove to be an interesting question. We have a composite function, and you'll see the chain rule come in here twice, meaning you'll have an extra kink than what you would expect, an extra kink in your chain. I want you to be able to view this question as if this square was kind of affecting the natural log and you had this x minus 1 sitting on the side, because this manner of looking at it this way will guide you how you make your initial substitution, which should be this. Your initial substitution should be a natural log of x minus 1. Therefore, the substitution function should be u square. Look at it in this way. And now you do your chain rule. Derivative with respect to u, you have a u square, and then the derivative of that u with respect to x, you have a ln x minus 1. Composite function here still. Look at this substitution. V is equal to x minus 1. Therefore, the function with regards to that v is ln v. Bring in another kink over here. Derivative with terms of that u, you have a u square, and then the derivative with respect to that v, you have an ln v, and then the dv with respect to dx, you have x minus 1 right there, x minus 1. Now you just have to do the derivatives here across, which is not hard. You have a 2u over here, ln v becomes a 1 over v, and all of this x minus 1 derivative is just a 1. It's easy. Now what you end up with is a 2u over v, and you just have to substitute. And when you substitute, this is what you get. Here's your u value, here's your v value. You get 2 times the natural log of x minus 1 divided by x minus 1, which is your v value, and you are done. An interesting question. So keep in mind, this was an easier topic. We looked at the derivative of natural logs. Keep in mind, for these very simple cases, the coefficient will always disappear and you'll always end up with the 1 over x. In slightly more complicated cases where you don't have a clear coefficient, you have to use a chain rule and you don't see things disappearing. Here's another derivative we looked at, not commonly seen, but you have to look at this in the change of base formula, and you get 1 over x ln b as you do the derivative of that. And then the power function you see is this, b to the x ln b. I didn't present very many questions related to the power function, but maybe I should have. Maybe I can just present one more question with regards to this power function, then we end with that. And let that be the last question. Okay, let's look at this. If someone asks you to find this derivative with respect to x, and your question is bx ln x minus 1. You know you have to look at the product rule over here, the product rule, and you know you have a composite function, and let's proceed with it. You'll have here's your f function, here's your g function. You'll have the natural log x minus 1, your g function, multiplying by the derivative of the f function plus the derivative and the non-derivative, the unedited f function, multiplying by the derivative of the g function, which will have to be a chain rule. If u is equal to x minus 1, f of u is equal to ln u. So let's bring in that chain rule right over here. Let's bring it in right over here. Derivative with respect to u, ln u, and then the derivative of u with respect to that x minus 1. Now solve it out. You have ln x minus 1, derivative of b to the x will be bx ln b plus b to the x multiplied by 1 over u multiplied by a 1. And 1 over u is going to be a what? B to the x times 1 over u, which was 1 over x minus 1. Now look over here, common term b to the x and b to the x. There's no other common term. You can isolate b to the x and you can get over here ln x minus 1 ln b, right here, this ln b, plus 1 over x minus 1, and you are done. And this right here will be your final answer. So with that last question over here, now our truly last question, we end our video. And I hope you enjoyed this video. It was a quick, easy, swift topic, nothing too elaborate or complicated with this. I ask you all just to remain tuned to my channel. There are many more important videos coming up. Thank you for watching. Have a nice day.